Now you see we are going to calculate the group delay. You know, whenever you are going to design filters, you will be having group delay, group velocity, phase velocity, all those things you will be seeing. And use what you should understand is whenever you're designing a filter at the particular design frequency, the group delay will be minimum. 400 at 400 megahertz, my group delay is very, very minimum. So that at that particular frequency, whatever signal you send, it is not delayed. It is sent as it is to the output without much delay. Whereas you see outside the band, the group delay is very, very high, which means the signals which are outside the design frequency will be delayed a lot before sending it to the output. Now, if you want to perform the RF budget analysis, I can find the budget. What is the SNR? Everything I can find. So, what is the input frequency? What is the available input power? Minus 30 dBm. So, I hope you know what is the meaning of dBm. So, dB, you know, it is converting my power into decibel scale. dBm means my reference is, see, for dB, the reference is 1 watt. Okay. For dBm, the reference is 1 milliwatt. Whenever I put small m, it means the reference is 1 milliwatt. If I use dBu, the reference is 1 microwatt. In antennas, we'll be using dB. In amplifiers, we'll be using dBm. So dBm refers to the reference is going to be 1 milliwatt. Whenever you're going to use noise analysis, you will be using dBu. So dBu is going to be 1 microwatt. That analysis is given here. You can see here. Output frequency is also in the same band. Output power is minus 31 dBm. Okay. So you see input is minus 30, output is minus 31 because you see 1 dBm is lost because of insertion loss. Insertion loss is 1 dBm. So we use the formula, right? So when you use this formula and calculate the insertion loss is 1 dBm. Okay. And the gain, see the transducer gain is minus 1. So this minus 1 dB is going to be the gain is minus 1 is going to be the loss, right? This minus 1 dB is going to be the insertion loss. So we will say it as gain is minus 1 dB. So insertion loss is 1 dB. And SNR is 77 dB. SNR, you know, it is signal to noise ratio for any object or for any device or any network. Whenever you are measuring its performance, we measure SNR. SNR will say signal to noise ratio. How effectively my circuit can reject the noise signal. So if I give signal and noise combinedly to my circuit, it has to amplify my signal only and it has to reject my noise. So that is the two functions your network has to do. That effectiveness is measured by a parameter called SNR. Ideally, SNR has to be infinity. SNR equal to signal by noise, right? So signal has to be large, noise has to be less. The SNR has to be ideally infinity. So practically, infinity is not a measurable quantity, right? So we like to have SNR should value to be very, very high. So SNR here is close to 77 dB SNR, which is ideal case, it is impossible. Okay, since we are simulating and finding this value of SNR is acceptable, but practically you can never touch the SNR can never go more than 15 or 20 dB. That itself is going to be a very, very huge value for SNR. Okay. So this is one example which I want to demonstrate in high frequency analysis.